Hello community! Today we have a Python implementation here and we test the brand new QwQ-32B. So here we go, you are live. This is the real speed here of a Sudoku 16x16 with a specific algorithm here in Python. It goes out. Wow, this is amazing. I have to read this slowly because, yeah, Knut algorithm X, yeah. This is impressive. It seems that the algorithm is trying to find a solution because I'm doing this test and I know there's not really here on the internet a Python implementation. I've seen one C++, but you know there is an implementation that says here important limitation as a code switching or recursive reasoning loops. So yes, so of course I focus on this. Look, nice. So for the next 16 rows, it doesn't print out all the rows. This is a nice insight into the argumentation. Look, it's trying to build its first code segments. I just hope we get here the complete final code. I don't have to pick and choose. Okay, more code. Okay. This is just a rough sketch of the code. I need to fill in the details. QwQ, you are so cute. Okay, now I can map this replacement, set up the summary, find a solution. Yeah. Look, the approach, the cover, the Sudoku solver, and a Python code. Nice, I get really the complete Python code as expected. This is an open source free model that you can run locally. I run it here on the cloud-based version because I want to go here in the full accuracy. I don't want to have a scaled down version and a quantized version. I want to have the full thing because, as you can see, this is not an easy task. So explanation, node and column classes, dancing link classes, solve Sudoku function. So let me tell you, this is really impressive, but let's go step by step. Do you know what I like about this? Because it gives you here exactly the understanding. O1 does not tell you why. So let's have a look at this. So I've been asked to implement a Sudoku solver in Python that can handle higher order, like 16x16, using the dancing links algorithm. I'm familiar with Sudoku and how it works on the standard 9x9 grid, but higher order puzzles are new to me. I'm not exactly sure how it works or why it's suitable for Sudoku. I need to understand what higher order Sudoku puzzles are, says the AI. I know that the standard Sudoku is a 9x9 grid divided. Yeah, that's for 16x60, I assume it's similar, but with larger subgrids. Yes, it's divided into 4x4 subgrids, each contain digit 1 to 16, and the same rules apply. Correct. So for 16x16, we have 16 rows, 16 columns, 16 subgrid, digit 1 to 16. Beautiful. I need to confirm this. Let me look it up. Yes, higher order Sudoku follow the same rules, but with larger grids. So for 16x16 Sudoku, it's divided into 4x4 subgrids and you use digit from 1 to 16. Now about the dancing links algorithm. I mean, I love it how this AI is telling you exactly what it's doing, you know? And this is an explanatory AI. And this is what I love, that it is not a black box and OpenAI gives you then a result. You don't know what's happening. Here I can also see and maybe learn what is happening inside of the AI. So AI goes on and says, I recall exactly Knut's algorithm X, yeah, which is a recursive depth first algorithm for solving the exact cover problem. Correct. Can be modeled as an exact cover problem. Yes, where you need to select a subset of possible placements in each, yeah. Particular way implement using a double link circular list, which allows for efficient removal. So I use dancing links for Sudoku. What a coincidence that I've chosen this. So I need to model the Sudoku problem as an exact cover problem. Correct. This means that defining the constraint and a possible placement that satisfy these constraints. I think about the constraints for a Sudoku puzzle. Each cell must contain exactly one digit. Each digit must appear exactly once in a row. Correct. Each digit must appear exactly once in each column, and each digit must appear exactly once in each subgrid. So for the standard 9x9, there are 9 rows, 9 columns, 9 subgrids, and 9 digits, leading to 81 cells for 16, yeah, so 256 cells. Correct. Exact cover formulation, each possible placement of a digit in a cell is a candidate solution, yeah? So for each cell, there are 16 possible digits, so we have 4K. Yeah, okay, 16 times 6, so 256 times 16, it's the same. So each possible placement corresponds to choosing a particular digit for a particular cell. Now, each possible placement affects multiple constraints. Correct, it satisfies that the cell contains exactly one digit. Yeah, yes, all four are correct. So for each possible placement, we need to specify which constraints it satisfies. The number of constraints is 256 constraints for cells, yeah. 256 constraints for each rows, yeah. 256 constraints for each column, yes. 256 constraints for the subgrid, and in total we have 4 times 1000 constraints. So there are 4K possible placements. So the exact cover problem has 1024 constraints and 4096 candidates. Yes, you got it. This seems manageable. I love this comment. I mean, this is cool. And AI goes on. So now in the dancing link implementation, we need to represent this matrix of constraining candidate and efficiently manipulate it during search. But implementing dancing link from scratch can be tricky, especially since it involves manipulating a double linked circular list in a way that allows for efficient removal and restoration. Yeah, I recall that in Knut's paper, he describes the algorithm detail, and there are several implementations online, but I need implemented in Python. You are correct. Python isn't the fastest language, yes, I know, but I want Python and not C++. I need to think about how to structure the code. Nice. An AI that takes time and at least gives me a pattern that it learns, that is trying to, I need to define the structure of the dancing links node. Each node should be part of a doubly linked list, both horizontally and vertically. I can create a class for the node class with attributes for the row, column, and the link. Yep. Yes, I need to find a way to represent this efficiently. I remember that in Knut's paper, he suggests using a header node for each column and then linking the node. Yep. Since most of the matrix is 0, yeah, it's essential to represent it as a sparse matrix, correct? I can represent each possible placement as a list of columns, indices that it covers. Yep. The dancing list algorithm can work by selecting a column, choosing the row that covers the column, and solving the reduced problem. You see, it just goes through the problem, has its problem itself, finds solution. Nice. Inefficient in Python, yes, but I want to see the Python solution. I can look for existing Python libraries that implement. No, I want to see the code. A quick search reveals that there are some implementations available, but I'm supposed to implement it myself. Yes, you are right. I kind of like this model, you see, because I understand what it is doing. It is kind of a trust vector that is established. So I need to proceed with my own implementation. Absolutely correct, QwQ. So let me try to outline the steps. You see, I understand what the system is doing. Define the constraints, cell constraints, row constraints, column constraints, and subgrid constraints. Yes. Define the possible placement. Each possible placement corresponds to choosing a digit for a cell. Yeah. Each placement satisfies 4 constraints. Cell, row, column, subgrid represent a matrix where the rows are possible placements and the columns are constrained. Each row has 4 eyes corresponding to the 4 constraints. Yeah. Implementing now the dancing link structure. Create a header node, link the header node horizontally for each possible placement, create a node for each covered constraints, and then link them vertically and horizontally. Implement the procedure of the algorithm X. Yep, recurse, if the recurse succeeds, then return success. If no row leads to success, fail. That seems straightforward, but the implementation details can be tricky. Absolutely. Especially in Python, managing the links efficiently is important. I need to think about how to represent a matrix. One way is to have a list of columns where each column is a linked list of nodes. Yeah, it comes up with this. Yeah, each node contains a row index, the column index, then left, link to the left node in the same row, right, link to the right node in the same row, up, link to the node above in the same column, and down. Yeah, exactly. You see, simple. Additionally, each column has a header node that acts as a sentinel for the column. So the header node contains now the size, the number of nodes in the column, and the name. And now QwQ comes and says, this way, I can efficiently remove and restore columns and rows. But managing all these links in Python might be error-prone. Perhaps I can represent the columns as objects and the node as objects linked together. Alternatively, I can use dictionary, to map from nodes to their neighbors, but that might be too slow. Wait, maybe I can represent each node as an object with the attributes for left, right, up, down, row, and column. Yes, then the header nodes are special nodes that represent the columns. So therefore, the system tells me now I need to initialize the matrix by creating all the possible placements and linking them appropriately. Let me try to think about how to map the possible placements to the constraint. You know what? I like QwQ because it opens up the avenue to understand what the AI is trying to do. If you have a proprietary black box like OpenAI, I have no idea what's going on. But here I can see if I would have to correct something, exactly the place I can correct this because I understand the logic behind the argumentation. So QwQ goes on. First, I need to assign unique identifiers to each constraint. Cell constraint, row constraint, column constraint, and the subgrid constraints. Yeah, I need to figure out how to index these constraints uniquely. Perhaps I can assign a unique integer to each constraint. For example, the cell constraint would have an ID from 0 to 255, the row constraint from 256 to 512. The column constraint goes an ID from 512 to 767, and the subgrid constraints goes from 768 to 1023. Then each possible placement will cover 4 constraints, So I need to calculate the exact ID for each of these constraints. For example, for us, correct. I need to determine which subgrid a cell belongs to. So for 16 times 16 Sudoku, there are 4 subgrids. So the box constraint, starting, in the row constraint, it goes now to 1K constraint. Now for each possible placement, I need to link the node corresponding to the 4 constraint it covers. So we do the same exercise again. I need to create nodes for this constraint and link them together. For each possible placement, I need to create such nodes. In the dancing link structure, I need to have a header for each column and then link the node in each column vertically and link the node in each row horizontally. So for each possible placement, I need to create a row of nodes and each corresponding to one of the 4 constraining columns. Then link these nodes horizontally and also link them vertically to representative columns. Yeah, as you see, it's so easy if you have not lost here the argumentation per QwQ. When I cover a column, I can remove that column and all rows that cover it, which correspond to choosing a particular placement and removing all other placements that conflict with it. Implementing this in Python requires careful management of the links. I need to define a class for the node, Then I need to create a header for each column, which is also a node object, but with additional size attribute. Shows me the code, and then I need to link all the header nodes horizontally. Then, my goodness. So it goes on. I like the comment. This seems manageable. But implementing this correctly is crucial, as any mistake in the link management can lead to incorrect behavior. It even understands the sensitive part. Now, is this just learned behavior? Is this just playing with me? I don't know, but I like the way it opens up itself and it kind of shows me here the argumentation. I found a Python implementation of algorithm X on Wikipedia, but it's a bit different from the dancing link approach. Dancing link is always essential to implement X, I can find a way to represent the Sudoku problem in a way that's efficient in Python. Let's think about how to represent it. So to Sudoku grid, I need a way to represent I need a way to input the Sudoku puzzle, specify which cells are pre-filled and which are empty. So easy, no? 16 times 16 Sudoku, it's convenient to use the digits from 1 to 16, possibly using the ladder for 10 to 16. I treat them as integers, yes, of course. Then I need to process this grid and set up the exact cover problem accordingly, yes. This will reduce the search space significantly. Let's think about how to implement a cover and uncovering operation. Yes, uncovering a column involves restoring everything that was removed when the column was covered. I think I don't have to read this now step by step, but this looks exactly interesting and the right way to go. Now the question is the code implementation, choose the column with the smaller size. Is the code implemented, correct. Perhaps I should look for a more detailed explanation of pseudocode for the dancing link algorithm, so they're still not sure. I mean, is it really doing here research? Is it really connecting to the internet? Is this possible? Upon further research, is this just a pattern that it learned, or is it really doing research? I don't know yet. I found that in dancing link, the matrix represented as a double linked list. We know this. Covering now, yes, so it goes on. Need to define the constraints. Summary, the steps are. Okay. Define the constraints, define the possible placements, set up the exact cover matrix, yeah, implement algorithm X, okay, map the solution. Yeah, the backtracking, but okay. I need to process step by step, ensuring it's correctly implemented. Final solution. So and now it comes, this is also nice in the representation, highlighting, yep, solution is a Python implementation of a Sudoku solver using the dancing links algorithm. And then gives me all the parameter and then the solution code. So I don't want to look at the code. I just want to see, is the code working? Oh, I just have here a 4x4 grid example. Okay, yeah, just for demonstration. Okay, you know what we do now? We just input this code in an IDE and we see if it is running. I don't know anything else. I just want to, is it operational out of the box? So in a simple Python notebook, everybody has access to. I just copied the Python code, I inserted here the Python code, and I said go. So let's see what we get. We get an error, immediately an error in line 46 here. Okay. Next step, explain the error. And I clicked on explain the error, and then I get here in my free Colab notebook, please explain the error. So attribute error, the non-type object has no attribute down. Now Gemini comes in and tells me hypothesis. The error message here arises with the add error function in the dancing link clause. This means that you are trying to access the down attribute of an object that is none. This most likely happens because this is none. This can occur in the scenario where it presents some column header. Yes, initially, yep, then yeah, okay. And then I have my suggested changes to the code. Yeah, I see, okay, nice, else, yeah, okay. Explanation of changes. Nice. This is free. This is absolutely free for everybody. So you understand working with the system, what's happening, what are the solutions to this problem. But I just wanted to show you, is it possible to generate a code for this? And unfortunately, the answer is no. I do have to go and apply here corrections. But you know what? Let's go and ask here from OpenAI 01 if it could detect some problems in this code. Then we have a direct comparison from this system to 01. Let's do this. So here we are now in my ChatGPT 01 preview. I just inputted the code, nothing else. And I just say validate if it's a valid code. And after 47 seconds, you see 01 comes back. I'll be happy to validate your code and point out any issues with the corresponding. Yep. Review of your code. Upon reviewing the code you provided, this is the code from QwQ, I noticed several issues that prevented from correctly implementing the DLX algorithm and solving a higher order Sudoku puzzle. Below I explain the problems and provide guidance how to fix them. This is nice. Issues identified. Okay. Now OpenAI against Qwen. Incomplete and incorrect implementation. Missing recursion in the solve method. Should be recursive to explore all possible combinations. In your code, solve does not make recursive calls, which means it cannot backtrack and try alternative option when a dead end is reached. Okay, solution. Implement recursion in the solve method to allow the algorithm to backtrack and explore. Yeah. Incorrect handling of cover and uncover operation. Interesting. The cover and uncover methods may not correctly update the links between the nodes, leading to incorrect removal and restoration of constraints. Solution. Ensure that these methods properly adjust all pointers when covering and uncovering nodes. Real nice. You see, 01 detected this just by looking at the code. Nice. So simplified for a 4x4 grid. Okay, the example was given just for a 4x4, but I can understand, yeah, the code needs adjustment to handle a 16x16 grid. Oh, this is now interesting. It needs adjustment. I just thought this is a demo for a 4x4. Modify your code to support a 16x60 grid by updating the grid size. Okay, yeah, okay, this is no problem. Incorrect mapping of the solution back to the grid. The way you collect and interpret the solution from the DLX algorithm may not correctly reconstruct. Maintain a solution stack to keep tracks of chosen nodes and map them accurately back to the grid. Interesting. Correct implementation. Yippee! To address these issues, I provide a corrected version of your code that implements a recursive solved method, correctly handles the cover and uncover operation, adjusts the code to solve a 16x60. Okay, yeah, it's a demo. And this is important, probably maps the solution back to the grid. Due to the complexity and size of a 16x16, running this code may require significant computational resources. I have a free Colab notebook, that's all you get. And then I get the corrected code. Real nice. So, just from this state here that we are now, I can say the explanation of a coding problem in QwQ is exceptionally good. It is unbelievable precise. I understand what is going on. I can see the loops that the system is trying to argue its way around to find a solution. But unfortunately, just from a single example that is not a representative sample, I have to say it failed to generate a code that is running out of the box. Yes, of course, we can use now everything from cursor to whatever to correct the code, or even you see in Gemini it is correcting the code, or you go to O1 preview and it is correcting the code. But it is not perfect. Of course, it is only an experimental prototype by the Qwen group. But you know what? The explanation part alone makes it so impressive that for sure, maybe just to understand what is happening in the code, I will use QwQ, and I'm looking forward maybe for the next iteration for a real improved code implementation. But here we have now ChatGPT O1 preview. And as you can see here in my account, gives me here the corrected code. Yeah, we could run this now and see if it's really working. But I just wanted to explore here the power of QwQ, and I have to say, real impressive. Although maybe we can, or Qwen can improve here on its coding reliabilities. Nice. Okay, yeah, just have a look at this code. But I think let's stop here for this video. I just wanted to give you a first code impression. So if you use it, maybe there is some adjustment for the code, but the explanatory part, what is happening, how it is building the code, the logic behind the code, I have to tell you, real nice implementation. I hope you found this video interesting. I hope there were some new aspect to it, and it would be great to see you in my next video. Hey, there's also an explanation of the corrections. Isn't this nice? It's now recursive and correctly implements X, contains a solution list to keep track. Yeah, beautiful. Cover and uncover operation are updated to correctly adjust the pointers in the doubly linked list. Adjustment to 16, okay, correct mapping. Okay, after finding a solution, this information is used to reconstruct the solved Sudoku grid. Provided it's partially filled, the code we implement using the DX, solving computation intensive. Usage instruction, nice. Run the script, Python 3, okay, yeah. Adjust the puzzle, you can replace it, okay. If a solution is found, the grid will be printed in a formatted manner. If no solution exists, an appropriate message will be displayed. Recursion limit is increased to 100,000 to prevent an error. Solving large Sudoku puzzle with the LX can be time-consuming. Be patient while the algorithm searches for a solution. Conclusion, your initial code had the right idea but missed crucial components. Oh, that hurts, Qwen. This hurts. Missed crucial components for correctly implementing the DLX algorithm. The corrected code provided above addresses this issue and could be able to solve. If you have any questions about the code, please feel free to ask. O1, nicely done, nicely done, O1. See you in my next video.